Now let's discuss an important lemma of spectral radius. We've already seen that spectral radius is less than or equal to the norm of A for any norm and any A. But so it's a lower bound. But in fact, turns out that it's the greatest lower bound which you can have. But any matrix norm you have, this is the greatest lower bound which you can have. So let's state this lemma. Let A be an n cross n matrix, and we have an arbitrary small epsilon, which is greater than 0. Then there exists a matrix norm given by this function such that you find the spectral norm of A. This will be the matrix norm will be sandwiched between spectral norm of A and spectral norm of A. There's an arbitrary small quantity. So this is the tightest, the largest lower bound which you can find. Okay, this is what we have to prove. To prove this, let's try to prove this. To prove this, we have to use something like Schur triangularization theorem, which we'll discuss in detail later. Schur triangularization theorem. What it says is we have a matrix given a square matrix Cn cross n with eigenvalues lambda 1, lambda 2, etc. Lambda n. This could be repeated eigenvalues. Only that it's distinct. Okay, real or complex doesn't matter. And there exists a unitary matrix U. And what is the property of the unitary matrix? U into U transpose is equal to. So U into U transpose is equal to I. You look at the unitary matrices also in data, but we already know what unitary matrices are. Unitary matrix and an upper triangular matrix denoted by this triangle, the n cross n, with its corresponding diagonal entries as lambda i's, such that A is equal to any matrix A can be expressed as a U Hermitian. So this is actually a more specific case of what we have as similarity. This is similar. A similarity matrix being the unitary matrix. Okay, we'll discuss this later in more detail. So this is what Schur triangulation theory. We have a matrix A, square matrix A, in the complex domain with the eigenvalues lambda 1, lambda 2, etc., lambda n. Then we can express this matrix as a product like this, U Hermitian into an upper triangular matrix into U, where U being unitary matrix and the diagonal elements of the upper triangular matrix as the eigenvalues of A. Okay, we'll prove this later. But this we have to use for proving that spectral radius is the tightest lower bound. Okay. So for further proof, we have to do some constructions. We have to construct some standard matrices. not standard, some specific matrices so that we can prove this. Let's construct a matrix dt such that it has t, t squared, etc. Tn along its, this is a diagonal matrix, so it already has the diagonal entries. The diagonal entries being t, t squared, etc. to Tn, where t is some value which okay. Okay, how do we specify t? We'll look at it later. Now let's compute dt dt triangle dt inverse. So what is this triangle? This is actually the upper triangular matrix obtained by putting the eigenvalues of eigenvalues along its diagonal entries for a matrix A. Okay, so let's look at, before looking at the general case, let's try to see when we take this product for a 3x3 case, how will the final product look like? Okay, so for let's example, take a 3x3 case where we have t square t cube, the entries being 0. We have here we have triangle 1 1, triangle 1 2, triangle 1 3. Here we have triangle 2 2, triangle 2 3, and triangle 3 3. Rest is 0. And here we have inverse of this. So since it's diagonal, you just have to take 1 by t, or you can take it as t inverse t raised to minus 2, t raised to minus 3, rest of them being 0. Okay, so let's multiply this. This is dt inverse, this is triangle, and this is dt for the 3 by 3 case. So if you multiply these two, what you'll get, you will end up getting fine. T inverse. Oh, okay, what are these diagonal entries? These are lambda 1, lambda 2, lambda 3, right? Yeah. We'll end up getting lambda 1 T inverse what is the second term? These are all zeros, right? Write it more specifically so it will become easy. So here it will be 0 0. Here we have zero times this will be 0. This will be t inverse minus 2, delta 1 3, t inverse minus 3, lambda 2, t raised to minus 2, delta 2 3, t raised to minus 3, 0, lambda 3, t raised to minus 3. And here we have t 0 0 0, t squared 0 0 0, t cube. Further, if we multiply, you'll get lambda 1 0 0, and you get lambda 1 2 t raised to minus 1, lambda 1 3 t raised to minus 3. Here it's lambda. This is sorry, it's delta. Sorry, lambda 2, lambda 3. Here it's 0. It's lambda 2, 3, t raised to minus 1. Get a matrix like this. So if for a general case, we get dt delta dt inverse as along the diagonals, you get the eigenvalues, lambda 1, lambda 2, etc., lambda n. Here, it's an upper angular matrix, so all these elements here will be 0. And here you will get t raised to minus 1 into delta 1, 2, t raised to minus 2 into delta 1, 3, etc., t raised to minus n minus 1 into delta 1 n, etc. Here also you'll get t raised to minus n minus 1 delta n minus 1 comma n. Fine. This is how you get it. Fine. Okay. Now what we can see here is if we choose, so all these elements, the upper triangle elements, are multiplied by t, 1 by t or its powers, right? If we choose a large enough t, then the sum of absolute values of all upper triangular terms can be made arbitrarily small, it's less than epsilon. What I mean is, let's say uh, we take this t to a sufficiently large value, then all these values can be made very small, so that all of them will add up to a very small value, epsilon, right? So why are we using this? So in that case, what we can say is, if we take the uh, maximum column sum, dt inverse, which is the maximum column sum norm of this matrix, then what eventually you will have is, let's look at the first column, you will get lambda. Second column, you will get lambda 2 plus t inverse lambda, delta 1, 2, and etc. But lambda's modulus of lambda being the largest spectral value, we get rho a plus epsilon. This is the upper limit to this. Why? Out of all the modulus of lambdas, the spectral value, spectral radius will have the highest value. But out of all the sums, even if you have, let's say lambda n is the last, lambda n is a spectral radius, in that case, you will have all the other terms uh, along that particular column. But still, its sum is less than epsilon. So this is the highest value it can take. Okay. Fine. Now, let's define a matrix norm of B is defined in a fashion which is similar to what we had for so what we discussed in the similarity norm, right? If what we discussed, if A is a matrix norm, then we can define an S norm such that it is S inverse AS. This is also a valid norm. Okay. So here, this is all these things are actually constructions to make the proof happen. So if you choose dt of u B u inverse u Hermitian dt inverse. This is also a valid matrix now, where the similarity matrix being here, this is defined for dt. Okay, this is valid, or even dt u holding this, something like that. Here, this is the S, and this is the S inverse. That's what I'm trying to say. So this is basically, that's what I've told. This is dt, this is U Hermitian, dt inverse whole inverse into B into U Hermitian, dt inverse, matrix form of this. Fine. Okay. Now, let us find, this is for the generic case B, but let's find the norm, S norm of this. This is equal to norm of dtu into A into U Hermitian, dt inverse. But by Schur triangularization theorem, A can be expressed as U Hermitian, the triangle matrix U Hermitian, dt inverse. But since it's a unitary matrix, U into U Hermitian is equal to identity, so which gives you dt triangle dt inverse. We have already seen, yeah, here it could be any norm. Let's take the L infinity. Sorry. What norm? Let's take the maximum row, column sum row. Column sum norm here. Okay, so we've already proved this is less than or equal to rho times A plus epsilon. Okay. Fine. So this is rho times A plus epsilon, and we already know for any norm, this is less than rho times epsilon. So what we have is, sorry, rho times. So combining this one and combining two, you get okay, this is not true. This is actually S. We'll get norm of S is bounded between rho of A and rho of A plus epsilon. So it is the largest lower bound. So there are few things. What if we were taking another norm? Is it valid for any other norm or something? Yes, it is in fact valid, but how we prove this, I'm not really sure. We've taken, for this construction, we have taken L norm. What if we have some other norm? We get something to, I think we can try to prove this using some equivalence of norms that these conditions are same. If you are able to prove it using one norm, then you should be able to, it should be valid for other norms as well. Okay. So this is how we can prove that the spectral radius is the lower bound, but in fact it's the greatest lower bound of any matrix norm. Okay. Let's end this discussion then.